This is our presentation on macronutrient digestion. We are group 15. Now, to begin, a quick overview of digestion. This begins in the mouth as soon as we put food in there and start chewing. So our teeth are going to break down all three of our macronutrients through mechanical digestion. Teeth are really good at breaking things up. Our saliva will also begin to act on carbohydrates. We're going to talk a bit more about that pretty soon. But there are plenty of organs that help out in this process. The epiglottis is going to protect our trachea, that's our airway, during this chewing and swallowing. Food will travel through the pharynx, down the esophagus. The biggest way that food is transported at this point is through peristalsis. Now, this is unidirectional, meaning it goes in one way. It's also rhythmic, so it does follow a certain rhythm inside of your body, but it's completely involuntary and automatic. And it's the method by which your esophagus is going to push food through the alimentary canal. Now, once it goes through there, it'll end up in our stomach, where we'll see compression of food material. That's another form of mechanical digestion. Things get pushed together. We'll also see the food travel then to our small intestines. Now, in the stomach, we're going to have some acids, some other enzymes. In the small intestines, we'll see enzymes from the liver and the gallbladder, the pancreas. A whole bunch of things are helping out in this chemical digestive process. We'll also see the large intestine, which is where a lot of the absorption happens. The colon is the last part of your large intestine. It's going to reabsorb fluid and prepare that waste to ultimately be sent out the rectum. Now, in the lower part of your digestive tract, in our large and small intestines, the motion is going to be a segmentation contractions. Now, these can push chyme in either direction to help really break things up. Now, there are many chemicals that aid in the digestive process that are produced at various organs, as we had just talked about. And these all are equally important and necessary for absorption of simpler substances.
So for chemical digestion, here are some enzymes and other things that help out with digesting these macronutrients. For carbohydrates, an important one is going to be the salivary amylase, which starts in the mouth. Pepsin is important for proteins, and that's going to be activated by stomach acid. And for lipids, an important one that starts in the mouth, same as the salivary amylase, is going to be lingual lipase. So chemical digestion for carbohydrates, as said previously, starts in the mouth. Salivary amylase begins it, and it breaks down alpha bonds that hold starch together. Doing this converts carbohydrates into maltose and shorter polysaccharides. Only a small amount of starch molecules get converted into maltose and other polysaccharides. Strong acids in the stomach is what is going to inactivate amylase. So once that salivary amylase reaches the stomach, it's going to halt its breaking down of carbohydrates. In the small intestine, most of carbohydrate digestion occurs here. Pancreatic amylase is secreted into the duodenum and breaks down the starch completely. It turns it into many molecules of maltose, which is a disaccharide. Enzymes from the microvilli lining the small intestine then turn the disaccharide into monosaccharides, and these monosaccharides are glucose, galactose, and fructose. So, as previously mentioned, glucose, galactose, and fructose are the final products of carbohydrate digestion, and this happens with the three enzymes maltase, sucrase, and lactase. Maltase splits maltose into glucose molecules. Sucrase is what splits sucrose into glucose and fructose molecules, and lactase is the enzyme that splits lactose into glucose and galactose. Those glucose, galactose, and fructose molecules that were produced by digestion need to be absorbed by the body for usage, mainly for energy. Many of the monosaccharides are going to be absorbed in the small intestine, but some are going to enter the blood. This happens by facilitated diffusion. This facilitated diffusion happens in the enterocytes, and from there, the monosaccharides travel down the bloodstream through the portal vein. The portal vein goes to the liver. Once the monosaccharides are in the liver, they are turned into glucose molecules. Once they are all turned into glucose molecules. They're going to be returned back into the bloodstream. These glucose molecules can then be stored later for glycogen and fat. Glycogen is very important because it helps with regulating blood glucose levels. Carbohydrates that go to the large intestine are absorbed straight from the large intestine and used later for energy.
Next, we will talk about the digestion of protein. This, like all other macros, begins in the mouth when we start to chew our food. After it goes through the mouth, it passes into the stomach, where gastrointestinal juices begin to alter proteins. First, we see hydrochloric acid act to denature and unfold proteins. The pH of the stomach is roughly 1.5 to 3.5 due to this hydrochloric acid. We also see the enzyme pepsin, which acts to break down peptide bonds in proteins, especially hydrophobic proteins. And pepsin really relies on hydrochloric acid to be activated, as the proenzyme for pepsin, pepsinogen, is not active until it is exposed to that hydrochloric acid in the stomach. Now, we'll also see contractions in the stomach that help to convert that protein to chyme and sort of segment break it up. This chyme passes to the small intestine, where it is then altered by various enzymes. And in the small intestine, we see that beginning section of it, the duodenum, receives pancreatic proteases, chymotrypsin and trypsin. Each of these two enzymes acts to cut protein chains either at large for chymo or smaller for trypsin at these amino acids. So the size of what we're cutting, since there are some 24 different amino acids, we do need a lot of different enzymes to act on these. It's important to note that these pancreatic proteases are dissolved into this chyme and mixed in with it, whereas our brush border enzymes are suspended in the membranes of our microvilli. These are our peptidases, which do also help to break small peptide chains into these single amino acids. The biggest difference between pancreatic proteases and brush border enzymes is that pancreatic proteases help break large polypeptides into di and tripeptides, and from there they pass towards the brush border enzymes in the microvilli to be broken down into individual amino acids for absorption. So the final products and absorption of protein, as we talked about, we have those polypeptides being broken down into di and tripeptides. Now, very few of those actually do make it into the bloodstream. We do need to see amino acids. Now, 99% of all protein that we absorb enters the bloodstream as an amino acid. So there's not really much room for larger di and tripeptides. The process by which these proteins enter our body is through the enterocytes, which are those cells lining the intestines. And from there, we talked about those brush border enzymes, which help to break di and tripeptides into amino acids. Now, because there are so many different amino acids, a lot of them have their own or similar to each other pathways that each one takes. So some will rely on active transport using sodium and hydrogen co-transporters, whereas others will take part in facilitated or even simple passive diffusion. The process by which protein is absorbed is very similar to that we see in the absorption of our monosaccharides, as we had recently discussed. It's important to note that if certain proteins are not absorbed by the time they reach the end of the small intestines, no more will be absorbed in the large intestines. So anything that doesn't make it out, all that dietary protein will be lost in feces, provided it doesn't get absorbed into the enterocytes and then through the capillaries of the villi into the blood.
Chemical digestion of fats begins with the emulsification of fat into tiny droplets. This happens due to lingual lipase, which is an enzyme released with saliva. Next is gastric lipase, which begins the breakdown of triglycerides into diglycerides and fatty acids. In the stomach, churning and contractions disperse fat molecules. Fat then enters the small intestine as chyme, which signals the secretion of bile, and pancreatic lipase. Bile molecules, which contain hydrophobic and hydrophilic ends, prevent molecules from sticking together. Micelles are the combined structure of fat and bile molecules. Bile salts then coat and emulsify large fat droplets into smaller droplets, which allows more effective breakdown by lipase. Pancreatic lipase breaks down fat molecules into monoglycerides and free fatty acids. These pass through the small intestine and convert to triglycerides. Fat's final stage in the body are in the form of triglycerides, free fatty acids, and glycerol. The triglycerides combine with cholesterol, phospholipids, and protein to form chylomicrons. Chylomicrons are water-soluble due to their protein coating. These molecules enter lymphatic vessels through the lymphatic capillaries. Lacteal faculties transport in the microvilli, finally being absorbed into the bloodstream from the right atrium. These are our student contributions. Thank you for your time. Hope you enjoyed.